Good afternoon, everyone. Welcome to another session of the Network Seminar Series hosted by the Center for Network Intelligence at the Robert Boyle Center for Cyber Physical Systems, IIT. Today's talk is by Dr. Sanjeev Sood, and he will be speaking on bringing scalable millimeter wave networks and applications to the masses. Dr. Sanjeev Sood is an assistant professor in the Computer Science and Engineering Department at the University of South Carolina. He received his PhD from the University of Wisconsin-Madison. His research interest lies in wireless systems and ubiquitous computing, and his research work has been regularly published in top conferences such as MobiConf, Mobisys, Sigmetrics, NSBI, and Infocom. He is the recipient of many awards: NSF Career Award 2022, ACM Hot Mobile Best Poster Award 2021, two ACM Hot Mobile Best Poster Runner-Up Awards 2021 and 2022, ACM Ubicom Best Poster Honorable Mention 2021, and President of India Gold Medal 2012. Dr. Sanjeev holds 8 US patents with 8 more pending. He served as the TPC co-chair for IEEE Spheres 2020 to 2022 and ACM MMNets 2020 and demo chair for ACM Mobisys 2022. Before we move on to the talk, we would like to request the audience to subscribe to our Google group for information on future talks. You can also visit our website for more details. Finally, we request the online audience to keep your microphones on silent for the duration of the talk. And for questions, you may ask Dr. Sanjeev directly. For the in-person audience, we have arranged coffee at the coffee machine in the adjacent building. Please help yourself to continue conversations over coffee after the talk. Over to you, Dr. Sanjeev.
All right. Thank you so much for that kind introduction. And thank you to Professor Parimal Parak for the invitation. And hello, everyone. Good afternoon. Before I start, I just want to mention one thing. I don't want this talk to be a one-way street where I only talk and you only listen. So please feel free to interrupt me anytime you want, ask questions, don't hesitate. But if I'm running late, I may stop you. Don't mind, I'll be here after the talk. All right, so given the introduction is already done, let me get right to the point. So, Fan, how many of you here are excited about 5G is coming or 5G is already here? Pretty reasonable, but few of you are not, but I don't blame you. I work on 5G and even sometimes I don't feel excited about the way operators are advertising 5G as just sort of a high-speed connectivity, right? But what if I tell you 5G and beyond networks could be much more than high-speed connectivity? What if it can deliver services beyond what's possible today, from physical security to transportation to medical diagnostic? In our lab, we push the boundary of what's possible with today's state-of-the-art wireless system to bring cutting-edge applications in sensing, imaging, and healthcare applications to inexpensive mobile devices. Now, let's take a step back and briefly talk about why are we discussing about 5G today. Well, global demand for mobile data has been skyrocketing, and 5G promises to meet that demand, right? Back in the year 2020, when 5G base stations started to pop up, there were about 190 million subscribers in the world, which is expected to increase about 7 times to 1.3 billion in just 3 years. And within 4 years, this amount of subscribers is expected to grow up to 10 times to 1.9 billion users. Right? One of the key enabler of 5G is this millimeter wave technology, a tiny antenna that works on a very high frequency and wide bandwidth. And over the year, as 5G gets rolled out, we expect this kind of millimeter wave technology to be ubiquitous very soon. What's so special about millimeter wave? Well, millimeter wave operates at this very high frequency and wide spectrum. Wider the spectrum, more the data rate, more traffic, more service can be enabled. And think wireless spectrum, the width of a wireless spectrum as kind of the width of a highway. Wider the highway, more traffic can pass through, right? And with that, take a look at the current highway width at today's LTE and Wi-Fi. On the spectrum scale, if I plot the amount of spectrum we are using at LTE and Wi-Fi is literally this much. And compare that with how much wider spectrum we have at millimeter wave. Between 30 to 300 gigahertz, we have more than 1,000 times wider spectrum. And wider the spectrum, more the data rate, more services could be enabled, more Internet of Things devices could be supported, right? And 5G plans to use both this LTE and Wi-Fi. And in fact, today's commercial device using just 2 gigahertz spectrum slice out of that 5G spectrum can already achieve 7 gigabit per second wireless speed rate. This is pretty exciting, and not just high-speed connectivity. Millimeter wave has been used for a very long time by satellites for weather forecasting, for remote sensing, has been used by US military for covert communications, and also are currently being used by airport security scanners used by TSA. So we imagine that given this millimeter wave technology would be ubiquitous soon, we can potentially enable many new Internet of Things applications that we have never thought before. But rather than me telling you what's possible with millimeter wave, let me try to demonstrate you. So here I have a millimeter wave device, and the center is where the millimeter wave antenna exists. The size of the antenna is literally the grain of a salt. And this antennas will be used to communicate with the 5G base stations, will be used to communicate with your 5G home wireless routers. And in fact, what I'm going to do, I do have another copy of the sample, which I'm going to use for demo. I will pass this sample around just for you to take a look on the device more closely. Would you please take a look and pass it around? Maybe I will just. Right. While you guys are taking a look at those samples, let me try to set up the demo. Live demo is always challenging, so fingers crossed. All right. Oh, let me try to zoom out a little bit so you can visualize a bit better. Okay, so what is being plotted here in live? I'm collecting the data from the sensor, and the sensor is here. The antenna is facing upward, and on the x-axis, we are showing the distance of different objects reflecting millimeter wave signal back to the device, right? So you have different objects exist at different distance from the antenna. The objects could be ceiling, could be my body, could be table, the chairs, and so on. And the distance is on the scale of or unit of millimeter. So a distance of like 3,240 millimeter means 3.2 meters, right? That is the x-axis. The y-axis shows the strength of millimeter wave reflections coming from different parts of the object, right? Higher the strength means different objects, that object at that distance is reflecting signals very strongly, right? And you can see that there is a very high sharp peak around what, 1.8 meter away from the millimeter wave device on the table. Can anybody tell me where is this very high strong reflection coming from? What? Yeah, the ceiling. You're right. Yes, the ceiling is, I think, made of concrete, is reflecting the signal very strongly. While on the other hand, other objects, potentially maybe the projector, the screen of the projector is reflecting signal, probably reflecting it very weakly. And in fact, you can actually demonstrate that if I just place my hand on top of the antenna, right? You can see my hand actually absorbs the millimeter wave signal completely, so that the device cannot transmit the signal towards the ceiling and cannot get a reflection, right? And in fact, not just a movement of hand, I can even move my hand a little bit, and that is going to be also interpreted by the device itself. Okay, in fact, I can do a better demonstration if I plot a two-dimensional view of this signal. So what is being plotted here is the same previous plot. X-axis is the different reflecting object. Y-axis is the strength, and the Z-axis toward the screen is measurement across time. So I'm plotting multiple snapshot of measurement across time. And in fact, millimeter wave devices are so sensitive. If I take my finger and do a millimeter scale finger movement, you can see that movement is going to be very prominent as at a potentially distinct signature on that reflection. So I can do a different gestures. I can block the device. I can move my hand in a different way. And you can immediately imagine that you can build all sorts of new cool Internet of Things applications, spatially related with human-computer interactions, where you don't have to literally touch a device, and you can actually interact with the device remotely without touching them. Like, for example, creating a bigger virtual screen for a small smartwatch, where you don't have to touch the smartwatch and you can interact and control the smartwatch on the air. Right? Any question up to this point? Any question, thoughts, comments? Pretty much clear to everyone what's been happening here. And in fact, these are the wireless signals. So the fundamental principle of this device are not dependent on the light condition. So if I turn off the light, this device is still going to operate, right? Because you still get your wireless connectivity if you turn off your bedroom light, right? So in other words, these are sort of invisible wave that you cannot touch and feel, that you can literally interact and build new Internet of Things applications. Okay, so with that, let me stop the demo and go back to my slides. Okay. In our lab, we use this kind of invisible waves to build a disruptive Internet of Things application. We use a mathematical model, signal processing, and deep learning tool to extract intelligence from those wireless reflections, which in turn can be used to build ubiquitous sensing modality. We have used these waves to build applications like monitoring vital signs remotely without putting any sensors on a user body. So for example, if someone takes a breath, inhale or exhale air, there is a chest movement, and that movement could be interpreted by the reflected signal. And based on that, you can measure someone's breathing pattern, even heart rate, without putting any sensor like Fitbit or smartwatch on the body. We have used these ways, of course, to detect micro gestures and micro activities, just like the one I mentioned, like detecting millimeter scale finger movement and using that to build a human-computer interaction application. We are currently using these waves to understand different material properties, even like understanding how fresh and how sweet a fruit is purely based on reflections coming from millimeter wave, from the object and from millimeter wave devices. Of course, we are using these waves to build a resilient network infrastructure by optimally placing the device, fast handoffing the connections between base stations to enable disruption-free connections for autonomous vehicles with roadside infrastructure. And also we are building 5G-like high-speed connectivity in the sky. Recently, we are using this wave to build a human silhouette shape, size, posture recognition system without using any camera in your home or in your bedroom. And this can enable many privacy, non-invasive monitoring applications like understanding activity of kids or activity of elderly person in assisted living condition, detecting fall, even monitoring sleep posture, like the way you sleep without actually putting any camera, which can be used to avoid like bed sore for patients recently suffering from strokes or surgery. And recently, we have used these waves to build applications in mobile physical security, understanding shapes of hidden objects like a gun within someone's pocket or bag. Again, because wireless signal can penetrate through certain material like cloth, it can be reflected through different metallic objects that could be hidden inside someone's bag or pocket. And we can use that to build the shape of an object. Now, as much as I'd like to talk about all this application in detail, in the interest of time today, I'm going to focus only on these two sets of application. But of course, I'll be very happy to talk about the other applications in more detail after the talk. Any question up to this point? Questions, comments? Yes. So millimeter wave has a various different frequencies. It works from 30 to 300 gigahertz. In our lab, we also use different frequencies, like one is at 77 to 81 gigahertz. Another is at 120 to 127 gigahertz. We have other devices that operates also at 5G frequency, like 28 gigahertz. So different frequencies, and also there is advantage of using different frequencies, like you get larger bandwidth in certain frequency, you get a better reflection in certain frequencies. So like why the rollout is being delayed? Yeah, of course. I mean, the concept of millimeter wave has been there for a long time. I think Professor Jagadish Chandra Bose demonstrated using triggering gun using a 60 gigahertz millimeter wave in 1900s, right? But I think the hardware was not mature enough, and now we are at the stage where hardware could be built, the antennas could be manufactured at a scale and at a cost that is where we are expecting this rollout. And of course, it also depends on how people adopt, right? When you show them a technology, many people may not adopt immediately, but with the advertisement about 5Gs and all that, we expect more devices, more millimeter wave devices to be ubiquitous very soon. Good questions. Any other questions, comments?
So how sensitive is it to the noise, especially like dust and smaller particles? Like fog?
A very good question. That depends on the frequency you are using, right? So if you have, if you're operating at like a lower millimeter wave frequency, like 60 or 70 gigahertz, I would say it's not that affected, like because the wavelength is on the order of 5 millimeter, and dust particle is much smaller than that. But if you're operating at like somewhere like 300 gigahertz, those can affect the reflected signal. In fact, many researchers have shown that you can actually use millimeter wave reflection to understand the properties of different gases within a chamber purely based on reflections. So yeah, it depends on the frequency that you use. Any other questions, comments? Okay, so with that, let me quickly jump onto the talk today. So first, I will start talking about the mobile physical security using millimeter wave to image an hidden object hidden inside someone's bag or clothes, and then I will talk about the monitoring vital sign. And in fact, there are many applications where imaging concealed object has been shown to be very useful. For example, understanding hidden structure like pipes, electrical wiring within a wall, understanding the how damp a wall is, like the moisture level, which are not visible through naked eyes, and it can be used to monitor inventory, like understanding if there are items missing or there are items damaged within a package without opening the package itself. And I'm sure some of you are already familiar with this kind of contraband detector in the airport. These are not metal detector. These are a structure where you go inside and spread your arm like that. And it actually uses millimeter wave antenna to understand if someone is carrying a contraband, like a gun or knife within their clothes, right? So we thought, like, given this millimeter wave technology would be ubiquitous soon, what if we can bring this hidden object imaging functionality to your commodity 5G devices like 5G smart? And this is where we propose our system called Squiggle Milli towards mobile physical security. And the kind of idea is, imagine you pull out your smartphone on your pocket, from your pocket, and it has a millimeter wave technology, and you squiggle over the object of interest, like could be a bag where you think potentially some contraband could be hidden, and it somehow can reveal the shape of a metallic object like a gun or big knife or pistol inside the bag, right? And that is the kind of end goal that we have for this project Squiggle Milli. Right? Now, before I talk about how Squiggle Milli works, let me first show you the kind of output that we get from Squiggle Milli, right? So, for example, let's say this is a pistol, a kind of, and if you take a camera image, this is what a vision camera would produce, and this is the kind of shape produced by Squiggle Milli, right? You may think that, well, what's the big deal? I mean, camera can do a better job. It shows many features of the gun. Squiggle Milli just shows the shape of the gun itself, and it's not even that good, right? So what's so special about Squiggle Milli? Well, the interesting thing happens is when the object is hidden inside someone's clothes. Okay, of course, camera will not work, and you cannot see what is hidden inside, but somehow Squiggle Milli can still reveal the shape of an object hidden. Okay. Now, there are a couple of challenges to enable this kind of hidden imaging, hidden object imaging functionality. I'll start with the challenges. One of the first challenge is to do with handheld imaging. When you're squiggling and scanning an object of interest using your hand, you cannot control the way user scans an object, right? There is a nonlinear motion involved. Also, there is a non-uniform sampling because you don't know some part of the object could be scanned more by the user than other. And there could be multiple objects which can reflect signal strongly. So you have to deal with multi-object reflections. What if one object is overlapping with others? You have to segment them up and all that, right? So traditionally, these problems have been solved by airport security scanner by placing those millimeter wave devices on an infrastructure and moving that precisely, right? They control the way the device moves, right? That's why you have to go inside the infrastructure, spread your arm, and it can scan your body. But when you're doing an ad hoc setting like handheld movement, you cannot control that. Also, there is another problem of specularity and weak reflectivity. Not all part of the object is going to reflect the signal equally, right? Those parts that are metallic probably will have a very high reflection, and those part that are non-metallic will have a weak reflections. And probably if you image something like a toy gun, in this case, you'll get an image like that. You cannot get a shape of an object here, shape of the real object here. And also, if the object is not perfectly aligned with the antenna plane, the signal that you transmit towards an object will get reflected some other direction, will never come back to the antenna itself. So the information about that part of the object is lost. What can we do? Well, the top challenge is mostly to do with the engineering problem, which we have solved, and I would encourage you to read our paper. This specularity and weak reflectivity is more of a fundamental challenge, which I'm going to focus for today's talk. Any questions, comments at this point? Yes. Cross range. Right. Very good question. That depends on the span of the squiggle itself. So, and also depends on how far your target scene is, right? Because there is a theoretical equation that governs, right? The farther you are, the cross range resolution is reduced. So we have tested on like squiggle around 20 by 20 centimeter grid, and you get a resolution about 4 centimeter in cross range. And of course, there are problems with non-uniform sampling and all that that exists already. Yeah, so about 4 centimeter at 1 meter distance from the object. Good question. Any other question or comment? Okay, so before I talk about how we solve the challenge, right? Let me first quickly talk about how we can construct a millimeter wave image from millimeter wave reflection, just like the reflection I was showing in the demonstration. Okay, so imagine you want to construct an image of a pistol like this. In this case, a millimeter wave antenna is going to send a broadband, wide beamwidth signal towards the object, and different parts of the object is going to reflect the signal back to the antenna, right? Just like the device sends a signal towards different parts of the room, ceiling was reflecting back. And interestingly, different parts of the object is at slightly different distance from the antenna. In other words, those parts that are far away from the antenna is going to reflect the signal later, and those parts that are near to the antenna is going to reflect the signal earlier. And if you use a wide bandwidth signal, you can actually distinguish different reflections in time in terms of their time of arrival, and you can measure the reflectivity coefficients. Okay. And if we can somehow measure those reflectivity coefficients at different points of the object, we have our millimeter wave image. But here's the problem. The measurement that we get is one-dimensional, but the target scene exists in 3 dimensions. So a question, is it possible to recover the shape of an object which exists in 3D using a measurement in 1D? Question for you. What do you guys think? That space also, right? But the problem is, given that the object is in 3D, many points on the object is going to reflect, and they are going to be mapped on the same range or time of arrival of your one-dimensional signal. Okay. So we believe fundamentally it's not possible to recover the 3D shape of an object using a one-dimensional signal. And for that reason, what we can do is not just measure the reflection from one point, you can actually move the antenna in 2-dimensional. And this is where the reason of this squiggle comes in. Why do you have to squiggle over an object of interest? And if you can squiggle over a 2D plane, each point you capture a one-dimensional reflection, you get a 3D spectrogram of a target field. Okay. And this 3D spectrogram then can go through a series of Fourier transform, a Fourier transform in time, Fourier transform in space, followed by different max filtering and inverse Fourier transform to give you a 3D shape of an object. Now, no need to worry about the exact detail about how this Fourier transform works, but take my words, there exists a well-defined method that can convert this 3D spectrogram to a 3D shape of an object, the 3D spatial information of an object. With that knowledge, if this is the camera image, this is the kind of image that we expect from the 3D spectrogram, and we get this kind of image. So where is the gun? Where is the shape of the object, right? So what's going on here? Well, you recall the challenges I mentioned? Challenges to do with non-uniform sampling, handheld motion, and challenges to do with specularity and weak reflectivity. This is where the images could be distorted, and you may not be able to interpret the image if you just use traditional imaging method over your measured 3D spectrogram, right? And one of the fundamental challenges is to do with specularity and weak reflectivity. Many parts of the object do not even reflect the signal properly. And also, if the object at millimeter wave frequency, because it operates at very high frequency, most of the object surface acts like a mirror. In other words, some of the transmitted signals towards the object will never reflect back towards the antenna. Let me demonstrate what I mean. Imagine an object is parallel to the millimeter wave antenna plane. If you transmit a signal, it will reflect back towards the antenna. So you have some information about the object, but if the object is slightly misoriented with respect to the antenna plane, if you send a signal towards the object, the reflection is going to go somewhere else. It's never going to come back to the antenna. And that information about that part of the object is lost. Traditionally, airport security scanner can solve this problem by, again, placing it in a precise positions by moving the antenna in a many directions across the subject. But we don't have the luxury when you do it using a handheld movement. So what can we do here? How do we solve this fundamental challenge with specularity and weak reflectivity? Thoughts, comments, questions? Again, don't hesitate to interrupt and show your ideas. What can we do? Well, this is where one of our motivation of using existing techniques in deep learning comes in. And specifically, we try to use one of the existing tool called generative adversarial network, which has been used in traditional image processing to improve the quality of low resolution image and convert it into a high resolution image. How many of you are familiar with generative adversarial network here, or GAN? Okay, not much, so that's good. Let me briefly talk about how a GAN works. In the GAN learning model, you are actually going to train two models simultaneously. One is called generator and one is called discriminator. The job of the generator is to take input of this low resolution, low quality image and try to find a mapping between low resolution to high resolution images and learn the mapping through thousands and thousands of data samples, right? At the same time, the discriminator is acting as a teacher to continuously judge how realistic the images, the high quality images are produced by the generator. Every time the generator outputs an image, the discriminator compares the output image from generator and a real high quality image and say whether generator is producing a generated image or a realistic image. And again, by doing this kind of training, converges only when the generator starts to produce a very high quality image such that the discriminator is fooled and it cannot differentiate between a generated high quality image and a real high quality image. In that case, we say that the GAN has been trained and has converged. So generator is constantly trying to fool the discriminator, and discriminator is constantly trying to discredit the generator, saying that it's not producing the realistic image. And this is where it's called adversarial training. They are acting as an adversary of each other. This is where the name generative adversarial network comes in. Okay. Mathematically speaking, what the generator is doing is taking an input data distribution, a low quality, low resolution image, and trying to learn a model that converts the low quality data distribution to a high quality data distribution. And the discriminator is taking the high quality data distribution generated by the generator and comparing with the true high quality data distribution and seeing how realistic the generator is producing high quality data. Okay. Any question? Somewhat clear? The actual details are, again, the devil's in the detail. But how do we use this kind of idea in our case? Well, what we can do is during the training phase, we can supply lots and lots of low quality distorted millimeter wave image and the corresponding ground truth image. Of course, the ground truth image is not going to be a optical image like this, RGB image like this. It could be a depth image which shows the shape of an object. And the generator is constantly trying to learn the similarities or the distribution similarities between the low quality image and the high quality ground truth and trying to converge into a high quality shape. And the discriminator is constantly trying to judge the quality of images produced by the generator. Okay. And by the time the network is converged, we expect the generator should be able to produce high quality shapes, even from this distorted shape like this. Okay. And at the end of the training, we can just use a generator and input the low quality distorted 3D millimeter image and should be able to produce the high quality shapes without any distortion, without the problem of specularity and low reflectivity. And the objects is going to be human perceivable. So this is kind of the architecture that we have used in our system, in our Squigglebili. We all talked about the generator and discriminator, which improves the quality of the 2D shapes generated by the millimeter image. And we also build a classifier that can classify different objects into discrete categories, could be a high risk items or contraband items. And also we have designed a quantifier that predicts 3D feature of an object, like the way orientation of the object, how far the object is located from the antenna plane and so on. Okay. With that, let me just give you some visual pictures, kind of visual examples of how the Squigglebili performs. But before that, I just want to mention that we don't have a 5G smartphone with millimeter wave capability today that can give us the millimeter wave reflection. So how do we test our system? For that, we had to use a prototype device from Texas Instruments. The device works at 77 to 81 gigahertz millimeter wave frequency band. And we can actually place the device on a mechanical controller to collect ideal ground truth image generated by millimeter wave signal reflection, like an airport security scanner. And we are by using a co-located depth camera. And we train our system using the ground truth and also test the quality of the shapes generated by squiggle milli. So here's a couple of examples. So in the top case, you have your pistol semi-occluded. You can see the butt of the pistol here from the optical camera image. And this is the kind of image you get if you apply a traditional imaging method, like the Fourier transform method that I mentioned. Compare that with what we get with squiggle milli. The shape is pretty reasonable, and you can see the proper orientation of the object. In fact, if the pistol is fully occluded, you won't be able to see using the visual camera. This is the kind of image that we get with the traditional method. Of course, given that I'm telling you there is a pistol, you can somehow make there is a pistol, but if I just show you this picture, there is no way to tell that there is a pistol hidden. This is the kind of shape we get. And not just for pistol, we have tested with other objects like a scissor hidden inside someone's clothes, and you can reveal the shape of the scissor also and compare that with the traditional image object. Recall that we have designed a classifier that can classify different hidden objects into discrete classes. We took the 10 different classes that are characterized by TSA, Transportation Security Administrator in the airport, as a high-risk object, like your explosive hammer, knife, pistol, and so on. And most of the objects, squiggle milli is able to classify them into their respective classes properly, except for very small objects like a screw, a small screw where it could be misclassified. And the reason is the screw is so small, the reflection strength is very weak. So the generated images are too distorted, and learning won't be probably able to reveal the shape of the object properly for small objects like a screw. But for big objects like a hammer, knife, they are classified pretty accurately. And these are the kind of shapes for various different objects that we have tested using our squiggle milli system. Any question up to this point? Thoughts, comments? Yes. Yes, it is a band of frequency. We are using 77 to 81 gigahertz frequency band. And that is used to create a depth image, right? You have to, we are trying to estimate the 3D shape of an object and project it on a 2D plane. So if you use a single frequency and squiggle, you probably won't be able to get a 3D shape. So you won't be able to get a proper orientation of the object. Right. That's a very good question. So what we believe is one kind of frequency band may not be useful for all kinds of materials. One of the reasons is different materials has different reflectivity properties, right? In this case, what we can do potentially, we can apply something like a hyperspectral imaging, where you just not use one specific frequency band, but use a chunk of frequency band at different frequency spectrum to create multiple images and combine them together so that it can reveal shape of objects that could be made of different materials. So something that we are currently working on right now is building a hyperspectral imaging by combining different spectrum of millimeter wave frequency band. Yeah, of course, yes, yes. And this is where more research, I think, has to be done. Even in an infrastructure-based method, the hyperspectral imaging has not been that explored yet. Good questions. Any other questions, thoughts?
This 3D imaging assumes that we know the position of the scanner precisely?
The assumption is user is controlling the device. So user can use like a internal sensor like IMUs and gyroscopes and accelerometer to self-localize the device as the user is squiggling over a area, right? So yes, you need to know the position, the pose of the millimeter wave antenna while you are collecting the reflected signal.
Is this accurate enough, the accelerometer that gyroscope, with reference to the millimeter wave?
It's not accurate enough because the error could be on the order of 5 or 7.5 millimeter on median across X, Y, Z axis, which could actually destroy or disrupt the image quality itself. But what we can actually do is, again, take help from this deep learning approach where we can train using those corrupted pose information and get a better picture or better shape, learning from this out of band optical information. So in our case, it's also very hard. Actually, you raised a very good point that it's also hard to collect all sorts of squiggle movement. You don't know what kind of motion a user will have, right? In that case, what you can rely on is a synthetic data. So essentially what you can train your system is you can synthetically generate millimeter wave reflections by emulating a target scene with a specific object, train your learning model with the synthetic data, and then fine tune with the real data collected from actual device. This is what we have done in our Squiggle Meet, right? In that case, you can account for many different variations of users' hand movement because you can actually simulate them. You don't have to really rely on actually measuring them in practice. Right? Any other question? Yes.
Not moving, right? So say in the real world, for example, certain computing is rarely in the Monte
Is walking by, yes.
So how well does it work when
Very good point. Yes, in this work we have assumed the object is static. So in fact, literally you go inside and someone without touching you can scan your body. That was the whole objective. And in fact, in practice, it can happen that someone walks into a shopping mall and the door can actually, while it opens up, you can actually put those devices on top of the door and the sliding motion of the door can act as like a scanning feature, right? In that case, this is again one of the work that we are working on. You can take help from reflections coming from part of the object itself, and also while the device is moving, you can account for the way user is walking towards the device. So in a way, you can get a partial scan. You can assume that the snapshot of the user as he is walking by, you can do a partial scan, and then as the user has moved towards the device, you can do another partial scan. So you can get a block of scan where individual blocks can be assumed to be scanned. But I agree with you, it's hard to combine them. So we are still thinking about a method to actually combine them and still get a reasonably focused image. But very good point. Yes. Without moving sensor, right? But that image is going to be mostly on the range in the depth, right? Because you are relying on only the bandwidth of the signal. You don't have any other information, right? So if you're relying only on bandwidth, you get a one-dimensional signal. So you have to actually use another dimension to get at least a 2 dimension. So 2 dimension can be mapped to a 2-dimensional signal. So you can actually scan it in one line or squiggle it to get a 3D shape.
So you have a bandwidth, then you can also use range migration algorithm or something that can extend to another dimension.
Very good point. But even the range migration needs at least one-dimensional movement. One single dimension bandwidth is not needed, right? Because it's again a mapping from 1 dimension to 2 dimension, which is like high mapping. Probably it's possible if you apply some out of band information, which you haven't explored before, something to definitely think about. Good questions. Any other thoughts or questions? Yes. Very good point. You can potentially use multiple antennas, but there is so many antennas you can fit in a small device like a smartphone, right? I mean, potentially if you change the entire side of the smartphone as an antenna, maybe you get enough resolution, right? But again, your smartphone is on the length of what? 10 centimeter, right? 10 centimeter at a 1 meter distance will give you a resolution of about 25 centimeter. 25 centimeter per pixel, right? And that's not enough for a small objects like that. So again, you have to move like around 20, 25 centimeter in space to actually create enough resolution. All right, so given that I'm running a little out of time, I'll just quickly switch gear and move to quickly talk about another set of application that we can enable with the millimeter wave signals, especially monitoring vital signs. And the whole motivation behind the project came in during the COVID-19 time. And as we all know that one of the hallmark of COVID-19 is reducing the lung functionality of a patient. And not just COVID-19, respiratory diseases like asthma, COPD, all are global health challenges, and the number of cases in worldwide and US is quite alarming. And mostly all these diseases can be characterized by reduced lung functionality of a patient. In other words, patients are not able to expel air out of their lungs during exhalation properly, right? So there is a need for a system that can continuously monitor someone's lung function, preferably at home. So what exists today? Well, there is a test called spirometry, which measures the lung functionality of a patient. So you literally go to a clinic, to a pulmonologist, and you sit down on a chair and you inhale air and forcibly exhale air in a contraption like this. And the spirometry devices can measure your lung capacity and various different indicators, right? So what kind of indicators? Well, there is an indicator there's a graph called flow volume curve and multiple lung function indicators. So on the left-hand side, you see a spirometry output of a healthy patient, in which x-axis shows the volume of air expelled out of the lung. In this case, the lung capacity is around 5 liters for a patient. And the y-axis shows the peak flow rate, how fast the user can expel the air. And for a healthy patient, you see a smooth curve like that. There is a peak, and then there's the flow rate is going to go down. And there are some key points which doctors use to interpret if someone is suffering from a lung disease. Someone suffering from like COPD, a chronic obstructive pulmonary disease, you'll see that lung functionality is reduced, the capacity is reduced, the flow rate is reduced, and so on, right? So doctors will use both this flow volume graph as well as the lung function indicators to understand if someone is suffering from a respiratory condition, right? And of course, what if we can do this continuously for asthma patients, continuously for COVID-19 patient, and track how their lung functionality changes over time, right? And of course, if you cannot do that in a clinical fashion because you have to literally go to a clinic, it's not possible to go there every day, right? Probably once in a month is fine, right? So the whole idea behind this project called MMPro came in with that idea that what if we can bring this in-clinic spirometry to your next generation 5G smartphone equipped with millimeter wave sensor. And the idea is, you recall that millimeter wave antennas, the reflected signals are so sensitive with a tiny bit of device movement. And imagine someone blowing air forcibly over a smartphone. That's going to create a tiny bit of vibration on the order of micrometer that is not visible through naked eyes, but you can process the millimeter wave signal and measure something like a phase of the reflected signal to understand how the device is vibrating. And the hypothesis is more forcibly a person is blowing air, more the vibration, more the change of phase. So there is a correlation between that, and potentially you can build a model to map that vibration signal back to the flow volume in the graph and as well as lung function indicator. That is a whole idea behind our project MMPro. I'd like to spend a little more time on how we can interpret this phase change due to vibration and how we can build such a model. So on the top, what you're seeing is someone blowing air on a millimeter wave device. There is a peak flow at around 3 seconds. And correspondingly, there is a change of phase of the reflected signals if you constantly measure the signal over time. And you may think that not much happening on this change of phase, but if you zoom in, you'll be able to see that there is a distinct vibration pattern happening on the order of micrometer on the from the millimeter wave antenna. And this plot shows the change of phase over time. You can even do a more feature analysis by understanding the vibration in both time and frequency. So you can measure the change of frequencies over time, and you can clearly see there is a distinct pattern appearing. You can measure when the person started blowing the air, when it stopped blowing the air, and there is a corresponding frequency change. So you can imagine that we can map this feature change or vibration properties and learn from the data and convert that back to this flow rates of a person, right? But there is a challenge. The relationship between different vibration parameters, two lung function parameters, are mostly nonlinear. What we are plotting here on the x-axis is a normalized vibration amplitude, and the y-axis is a peak flow rate of a person blowing air during spirometry test. And more the vibration amplitude typically means more peak flow rate, means if someone is blowing air more forcibly, you get more vibration. But of course, the relationship is quite nonlinear. So it's very hard to fit something like a regression model here to convert the vibration amplitude to a lung function indicators, right? So what can we do? Well, the idea is you can measure the vibrations not just from one antenna, you can measure it from multiple antennas that could be part of your smartphone. And then you need to convert that to lung function indicators. And for that conversion, what you can do is a series of convolution blocks that understand the spatial features coming from different vibration measured from different antenna. And not just a convolution block, we use something called LSTM. How many of you are familiar with LSTM here? Okay, LSTM is something like a recurrent neural network which sort of learns pattern in time. Just like convolution neural network learns pattern in space, LSTM learns pattern in time. And when you're analyzing vibration signal, which is a pattern in time, you have to apply something like LSTM block or recurrent neural network to understand how the vibration can be mapped to a lung function indicator, right? So this was the kind of overall architecture of our MMFlow. And again, we don't have a smartphone today with millimeter wave capability that can measure the reflection. So for that reason, we used a prototype device from Texas Instruments working at 77 to 81 gigahertz millimeter wave frequency band, which has 4 receive antennas. And for ground truth, we need to understand the ground truth lung functions. We use something called a flow volume calibrator, Jones FVC 3000. This is a kind of a gold standard device used to calibrate all FDA approved spirometry parameters, right? And we use this device to collect ground truth lung function indicators, as well as train our systems and test the accuracy. I'd like to show you some of the predicted spirometry flow volume graph from our MMFlow. On the left-hand side, you can see a flow volume graph of a ground truth flow volume graph of a healthy person. Again, the total lung capacity is around 4.5 liter, can achieve a peak flow rate of more than 10 liters. And if you apply something like a regression model, it's not able to capture or catch up with the ground truth. But on the other hand, MMFlow can track the ground truth accurately. And not just for healthy patients, for COPD patients, MMFlow can also track, while regression fit fails to track or reveals the lung functional indicators properly. Any questions, comments, thought at this point? We also tested the accuracy of MMFlow and compared the performance with FDA-approved handheld spirometer called one of the spirometer called MIR spirometer, and the average accuracy of predicting the peak flow rates, or in other words, the error from the peak flow rate is pretty much comparable to an FDA-approved spirometer. Interestingly, the maximum error is actually lower in MMFlow, because in MMFlow we already take into account the way user holds the smartphone in front of his mouth and the way user blows air. while the traditional method has no idea about the way user holds a device. And also, you need a spatial device, spatial hardware to do this kind of test. In this case, MMFlow, we can do it using a regular smartphone, which will be equipped with a millimeter wave technology. All right. So given that I'm pretty much running out of time, I'd like to wrap up this talk by saying a couple of things. The first thing is this is a really exciting time for wireless researcher. 5G is already here, but we have barely started scratching the surface with what's possible with 5G, especially with millimeter wave, beyond high-speed connectivity. In fact, researchers have already started talking about what would 6G is going to look like. And we expect 6G to be here around the year 2030. And you may think that 2030 is what, 8 years from now? Way too long time, right? But research for a cellular generation standard usually starts 10 years before it is actually implemented. So we are already behind the schedule in a way for 6G. And 6G also plans to use a very high frequency millimeter wave, something like 100 gigahertz or more than 100 gigahertz, and even frequencies around terahertz zone to achieve around tens of gigabit per second data rate per user all the time. But different from 5G, the architecture for 6G is thought to be a little different. In 5G, this kind of disruptive application I was discussing is thought after the fact, after the network is deployed. On the other hand, in 6G, we expect there will be a confluence of networking, sensing, and imaging all parts of the standard itself, right? To make the network aware at a global scale, at a city scale, at a more personalized human scale. Of course, malicious users will always going to be there. So lots of ethical, security, and privacy aspect of this kind of application needs to be thought, needs to be rethought, right? And with that, I'd also like to kind of give a shout out to my awesome PhD and master's and undergraduate student. All these works I showed are not possible without their efforts. And of course, I'd like to thank my sponsor, research sponsor, National Science Foundation, Texas Instruments, USA Aspire, and Vista Medical. And with that, let me stop here, and I'll be very happy to take any more questions. Thank you all. Yes. I'm sorry, what? So we are using phase ready. So you don't need to use a substrate to focus your beam. So we are using multiple phase ready antenna and using electronic beam steering and using phase to focus energy towards one direction. I think it should be something like, for this device, it will be somewhere like Rogers. I don't know the actual, what is the ID, but when you say radiation efficiency, could you elaborate? Sorry, I'm from more of a CS background, so if you use electrical term, I may not be that familiar with it, but could you elaborate what do you mean by radiation efficiency? Are you asking about losses, like insertion loss and all that? Oh, yeah, okay. Yes, but what I'd like to talk about the kind of range that we get, that is what end user sort of kind of rely on, right? So the range for this antennas that we are using for the demo can go up to like 15 meters. So around 15 meters, you can detect different obstacles, different reflectors, and different objects. The Texas Instruments device that I'm using can go up to range of about 50 meters, 50. So it has a much larger range because we are using higher transmit power. Any other questions, comments, thoughts? Yes. Yes. Close to the mouth. Yes. Very good question. Any kind of vibration or motion is going to affect the reflected signal. But what you can do is filter out those reflections in space and time. In space, what you can do is you can virtually create a boundary around your face, right? You can say that beyond 50 centimeter, I'm not going to use signal for any analysis, right? So you can actually literally chop off the signal out, which already removes all the reflections coming beyond a 50 centimeter sphere around your mouth, right? And you can also filter out in time. In other words, we expect the vibration to have a very high frequency, right? Compared to if a fan is moving, the vibration frequency might be in a different range of frequency, right? So you can apply something like a bandpass filter to basically focus on your vibration caused by your airflow, not by fan. Because when you blow air very forcibly, it has a very high frequency compared to a fan rotation. Good questions. Any other questions, thoughts, comments? Okay, so if not, let me stop here and please feel free to ask questions over email. Thank you all.
Thank you, Dr. Sanjeev, for an interesting talk. As discussed before, we would like to remind the audience to subscribe to our Google group for information on future talks. You can also visit our website for more details. Thank you and have a great day.